Hi everyone, my name is Shahram Kami from LTRAC Group at Monash University. This talk focuses on receptivity at the nozzle lip of underexpanded supersonic impinging jet. Underexpanded supersonic impinging jets classified as oscillatory flows. The self-sustained oscillations in this flow configuration is generally described by feedback loop. Feedback loop consists of four ingredients: shear layer instabilities growing in the shear layer region. They interact with shock, generating acoustic wave. They also interact with the impingement wall and generate acoustic waves. These acoustic waves are propagating toward the nozzle. Through the receptivity, they internalize into shear layer instabilities. Then, the receptivity in this content is internalization of acoustic waves into shear layer instability at the point here at the nozzle lip. The purpose of today's talk, the goal is characterizing the receptivity process. To do so, we define a transfer function, which is the function of acoustic source location, frequency, azimuthal wave number, and nozzle-to-wall distance. To find the nozzle lip transfer function, we use the non-modal linear instability analysis. We solve the linearized Navier-Stokes equation as an initial value problem in three-dimensional domain subject to the initial condition of pressure pulse. This pressure pulse allows us to excite a wide range of frequency. Instability analysis requires mean or base field. The mean or base field for this study obtained from time and azimuthal averaging of LES dataset of two cases. The case with nozzle-to-wall distance of 2 and nozzle-to-wall distance of 5, where the Reynolds number and nozzle pressure ratios are fixed for these two cases. If you are interested in dataset, please refer to this paper. For each configuration, we locate initial pulse at distance rp from nozzle lip and angular position of theta p from jet axis. We define a new coordinate, a straight line from source to lip, and a curved line in the shear layer. This is the example of the pulse located at 45 degrees. The simulations are performed in 3 dimensions. That means the pulse is a ring for azimuthal mode equal to 0. It's a sine wavy shape ring for azimuthal mode equal to 1. The time series are shown here. Pulse travels toward the nozzle lip through the receptivity, initiate the shear layer instability, and shear layer instability grows in the shear layer. We define the energy norm as this equation here. Then we calculate the energy norm in the new coordinate. We sample in this new coordinate. The reason is this gives us opportunity or flexibility to study other transfer functions if we're interested to find, for example, transfer function of shear layer or combination of receptivity and shear layer. In this study, we are interested in receptivity. Hence, sampling locations need to be close to the nozzle lip. Then we sample the data as input and output time signals at these two locations, which is shown here as an example. As already mentioned, we define energy of disturbances. We sample at input and output, then we move to the frequency domain by Fourier transform. If we calculate the cross-correlation of output signal with input signal divided by the autocorrelation of input signal, we can find the transfer function as a function of frequency. The non-dimensionalized frequency, Strohal number, is defined based on frequency, jet diameter, speed of sound, which commonly known as Helmholtz number. The other parameters of the study is radius of impulse location, which is kept fixed as a function of nozzle-to-wall distance h, which is 0.4 times of h. The other parameters or angular position of impulse, which is changed from 10 degree to 85 degree with the increment of 5 degrees, and the location of input and output. We also studied the azimuthal mode number 0, 1, and 2. Let's look at some results. The contour plot of Mach number is presented on this figure. Transfer function for azimuthal mode number 0, mode number 1, and mode number 2. To facilitate discussion, we define different regions based on the behavior observed in transfer function. The region A2 is defined between theta between 10 to 20. As you can see, transfer function is minimum, the maximum transfer function occurring at low frequencies. Moving to region B2, theta p between 20 and 45, the transfer function is maximum at high frequencies. The maximum transfer function, as we distance from the center line, is moving toward high frequencies. Moving to region C2, theta p between 45 to 80 degrees. Transfer function is boring, it's just function of frequency and is not changing as we distance from the jet center line. Moving to last region, D2, near to the infinite nozzle lip, the transfer function is maximum at straw hole numbers around 2 to 4. This is consistent for all three azimuthal mode numbers. Moving to next case, nozzle to wall distance of 5D. The transfer function also showing different behavior in different regions. A5 is defined between theta 10 degree to 15 degree. Transfer function is low, the maximum transfer function occurring at low frequencies. Region B2 defined as theta p between 15 to 85 degree. The transfer function is maximum at high frequencies. As we moving from center line of the jet, the maximum transfer function moving to higher frequencies. Region C5 is defined at theta p between 55 degree to 75 degree. As you can see, transfer function behave different in this nozzle to wall distance. They are maximum at low frequencies. As we distance from the nozzle center line, the maximum transfer function is moving to low frequencies. Moving to last region, which is D5, close to infinite lip nozzle, the transfer function is maximum for the first two azimuthal mode, and the maximum occurring at frequencies around 2, or non-dimensional frequency around 2 to 4. This leads me to summary and conclusion. The objective of this work was quantifying the receptivity process in underexpanded supersonic impinging jets. We utilizing the three-dimensional impulse response analysis by solving the linearized Navier-Stokes equation subject to initial condition of pressure pulse. Pressure pulse excited a wide range of frequencies. Azimuthal mode number, location of the pulse as an angular position from the jet axis, and also nozzle to wall distance are three parameters we consider in this study. We required the mean or base flow to define the linear operator A. The mean field came from the large eddy simulation dataset. The main conclusions are as following. This study showed the receptivity transfer function depends on frequency, location, and azimuthal mode of the acoustic source and nozzle to wall distance. The nozzle lip has a highest transfer function when the acoustic sources are located near to the infinite lip nozzle. For the nozzle to wall distance of 5D, the transfer function is also high at angles between 15 and 15. Happy to take questions. If you watch this as a recorded seminar, please feel free to contact me on my email address.